Vector graphics designs are composed of a layered collection of lines, curves, and polygons that can render at any resolution with no aliasing. It is common for vector graphics artwork to contain thousands of individual elements in the final design. Navigating thousands of elements is difficult, so vector artwork is grouped into layers, each of which can contain geometry or other layer groups. The vector artwork is then rendered by rasterizing geometry, starting from the background layers and moving to the foremost layer. Carefully creating a well-grouped layered representation is critical to maintaining the editability of vector artwork. This can be a very tedious or challenging process, especially on mobile devices or when importing data from another source, such as a PDF file. In this paper, we present an automatic method for arranging an unstructured vector graphics file with a flat set of layers into a sensible layer arrangement, resulting in a more natural and editable design. A strong indication of salient groups is recurring geometrically identical geometry. This commonly occurs because of the artist copying and pasting content, or using specialized tools such as radial repeat. As a first step, we detect sets of vector elements that are identical up to an affine transform. For example, in this kitchen scene, we detect the bags and spice bowls as identical recurring elements and immediately assign them into groups. To avoid undesirable merges, such as grouping all straight lines together, we require groups to have a certain minimal geometric complexity. At the core of our method is an agglomerative clustering method applied across all vector elements in the file. Agglomerative clustering is a bottom-up approach where each observation starts in its own cluster, and pairs of clusters are merged as one moves up the hierarchy. To cluster objects, we first need to estimate how likely any two objects are to belong to the same group, which we refer to as their group affinity. This might be based off factors such as their shape, size, color, and spatial position in the document. A critical indicator of group affinity that is specific to vector graphics is the containment relationship between vector elements. For example, the pupil shape is contained within the eye shape, which is contained within the face shape. This containment hierarchy is a very strong signal of group affinity. This can help group elements together that have a common shared containment parent, but are otherwise very distinct in attributes, such as color or shape. Vector graphics elements can be compared along many different axes. To compare color, we use the Euclidean distance between the LAB color space representation of the fill and the stroke colors. To compare spatial position, we consider the relative distance between object pairs against the average distance between other pairs in the artwork. To compare size, we use the object-oriented bounding box of the two shapes. And for shape, we compute a descriptor from the rasterized occupancy grid of the filled shape. We consider each axis independently, then linearly combine our overall scores to gauge the group affinity between pairs of objects. For more details of these descriptors, please see the paper and supplemental materials. Once we have a well-defined metric for group affinity, we proceed with agglomerative clustering. We start by finding the pair of objects with maximal group affinity, such as the two quads shown, and place them into a new group. But at the next stage, we will then need to compare this group of multiple elements against each other element in the file. We do so using a simple max linkage criteria, where the affinity between two groups of objects is taken to be the maximal affinity among all possible pairs of elements. Under this criteria, this group is more likely to merge with the trapezoid beneath it, on account of its similar size and shape to the elements in the group. We continue clustering across all elements and groups of elements, each time merging the pair with the highest group affinity. We terminate clustering when the quality of the best merge is below a threshold. Using the method we just described, we can take any vector graphics file and convert it into a meaningful hierarchical arrangement. This can greatly improve the ease of design for unstructured vector graphics files. We've implemented this technology as a plugin for Adobe Illustrator. Let's look at an example. We start with a flat vector graphics file, with each element as its own group. Basic tasks, like recoloring the keys on the keyboard or moving the calculator, can be very tedious in this representation because it requires you to individually select each of the objects that you want to edit. If you use something like a marquee to do a group selection, then you have to go in and manually deselect each of the objects that you didn't intend to select. Now we'll run our automatic arrangement algorithm on this file. This creates meaningful and salient groupings that facilitate many common editing operations and often correspond to human notions of the objects in the scene, such as the calculator, tablet, and cell phone groups. We have presented a method for automatically arranging elements in vector graphics files. There are many natural extensions to the method we would like to explore next. One natural line of future research is to explore using object detection technology to provide a strong object prior for the rasterized artwork. This signal could be combined with our method to produce clusters that more closely align with the human notion of objects. Secondly, we believe it is possible to study a large data set of artwork that has been grouped professionally by artists, and use a machine learning approach to learn a more robust notion of group affinity. This should allow us to form clusters that more closely match professional designs. Thank you for listening to our talk.